This topic is all about the energy changes that can take place during a chemical reaction. As you know, some reactions can be exothermic, which means they give out heat energy. Some reactions can be endothermic, which means they take in heat energy. This topic is all about looking at those two types of reaction in a little bit more detail. So we're going to start with a little recap about what the words exothermic and endothermic mean. An exothermic reaction is a reaction in which heat energy is given out by the chemicals. This causes the surroundings to get hotter. You would feel that if you held the side of a beaker which had an exothermic reaction inside, your hand would feel the warmth from the reaction. Endothermic reactions are opposite. They are reactions in which heat energy is taken in. So if you held the side of a beaker which had an endothermic reaction inside, your hand would feel cold because energy is being taken in from the surroundings. The next section here is on something called reaction profiles. Reaction profiles are basically simple graphs that you can sketch that represent the changes happening in either an endothermic or an exothermic reaction. So you need to know the look of this sketch for an exothermic and an endothermic reaction. In terms of the labels for the axis, the y-axis is labeled as energy, because we're looking at energy changes. The x-axis is a little bit strange. It's called the progress of the reaction. It's not really something you can measure in numbers, but basically the left-hand side of it is when the reaction has started. As you get further right, that's the reaction progressing towards the end. Now the first thing you need to plot on your graph is the energy level of the reactants. You normally do that by drawing a horizontal line and labeling it reactants. Then you want to show what's different about the energy level of the products in the reaction. Now, for an exothermic reaction, what we find is that the products actually have got a lower energy than the reactants, and for endothermic reactions, the products have a higher energy than the reactants. You can try to get your head around this by thinking about what an exothermic reaction looks like. In an exothermic reaction, energy is always given out, and that energy comes from the chemicals. So at the start of the reactants have got a lot of energy. The energy that is removed from the reaction causes the chemicals to lower their energy, which so the products have a much lower energy than the reactants. It's the opposite for endothermic. Heat energy is taken in from the surroundings during this reaction, and that gives extra energy to the chemicals, which is why the products have a higher energy value. The last thing you can label on this graph is the energy change value, which basically is the difference between the reactants and the product. What we'd say is the energy change for an exothermic reaction is going downwards. That gives it a negative value. The energy change for an endothermic reaction goes up. That gives it a positive value. One further point we can make about exothermic and endothermic reactions is for reversible reactions. So if the forward reaction of a reversible reaction is exothermic, you get it flipped when you go backwards. So the reverse reaction would be endothermic. That works both ways. If the forward reaction is endothermic, the reverse reaction would be endothermic. To see an example of that, this is chemical A going to chemical B. The forward reaction's got a minus sign. That means it's exothermic. But when you go backwards from B back to A, it goes to a plus sign, which means it's endothermic. But you notice the value of the number actually stays the same in both cases. Another thing that affects the energy changes in reactions is the activation energy, which is a phrase you've heard in other parts of the Year 12 course. The activation is the minimum energy needed for a reaction to occur. And what can happen is you could be asked a question where you have to draw a reaction profile, which we've already covered, but they can ask you in addition, on top of the graph, to show the activation energy pathway. It's not that hard to do, let me show you. So at the minute all we've got is a simplified version of the graph I've shown you before. Exothermic reactants above the products, endothermic products above the reactants. To show the activation energy, that's trying to represent the little boost of energy you need to give every single chemical reaction to get it going. So in both cases, you're going to draw a curve which goes up first and then drops down. So in both cases, we go up first and then down, up first and then down. The last thing you might need to label here is the actual value of the activation energy is represented by the difference between the reactant energy levels and the top of the peak of the activation energy. I've labelled them here as EA, which is sometimes used as a code for activation energy. This bit in activation energy ties in with another concept you've seen before in Year 12 chemistry of catalysts. Catalysts are chemicals that speed up the speed of a chemical reaction without being used up. Now, in terms of how they work, here's how you could phrase it. A catalyst provides an alternative reaction pathway of lower activation energy. And like before, you can represent this on a little sketch on a graph, similar to the graphs we've sketched already. So here we've got the sketch from the previous section for the activation energy being shown on an exothermic reaction. Remember, that's this little up and down bit we've got in the middle. Now, the line we've actually got here can sometimes be given a term. It's sometimes known as the reaction pathway. And if we compare that to what we've looked at the catalyst achieves, it provides an alternative reaction pathway of lower activation energy. So to show that on this graph, all we need to do is draw a separate curve, which is a separate reaction pathway, but make the activation energy a little bit lower. That will cause the chemical reaction to be quicker because there's less of a barrier for the energy requirements of the reaction. The next section revolves around you being able to explain in terms of bonds how a chemical reaction proceeds and what the difference is between an exothermic reaction and an endothermic reaction. So just looking generally, first of all, in any chemical reaction, you have got some reactants, which are some chemicals, and they make some different chemicals, which are called products. Now, in every single chemical reaction, two steps or two stages have to take place. The first step is that the bonds in the reactants have to first of all be broken apart, and that takes energy in from the surroundings. And the second stage is that new bonds have to be formed in the products, and that gives out energy. Now, the difference between an exothermic and an endothermic reaction is simply which one of these stages is bigger in terms of energy values. If you've got an exothermic reaction, you will get more energy out in step 2 than you had to put in step 1. But if you've got an endothermic reaction, you had to put more energy in step 1 than you get out in step 2. Now, what you can get in this section is a very common type of 5-mark question where you're given a chemical reaction, you're told it's either exothermic or endothermic, and you can be asked to explain why is it exothermic or why is it endothermic. It's a pretty repetitive structure to how you're meant to phrase that question. So here's an example. So here's an example of a chemical reaction between methane and oxygen to make carbon dioxide plus water. You're told in the question this reaction is exothermic. You now need to explain clearly why it has to be exothermic. So the first point is energy is taken in to break the bonds in methane and oxygen. So you're going to get 2 marks for this bit. First bit is you're showing off that you know that energy needs to be taken in to break the bonds in these reactants. The second mark is for you to clearly explain what the reactants are, so you should name them from the equation methane and oxygen. You need to make the opposite point for the products, so you'd say that energy is given out when the bonds are made in the carbon dioxide and the water. So again, you need to name the products where the bonds are being made. Your final point is just a comparison about which one of these is going to be bigger. As we talked about, in exothermic reactions, step 2 is bigger, the energy given out. And in endothermic reactions, step 1 is bigger, so energy is taken in. In this case, we've got an exothermic reaction, so we're going to say that the energy taken in the first step is going to be less than the energy given out in the second step. So your final mark is just to make a comparison. So if this reaction was the other way around, if this was endothermic, you would just say is greater than in this little step in the middle. The final section of this topic is a calculation that you need to be able to do to work out an actual value for the energy change of the reaction, whether that is an endothermic or an exothermic reaction. It's easiest if we explain this using an example directly. We're using the same equation we looked at in the last section. Methane plus oxygen goes to carbon dioxide plus water. Now, often in this question, to give you a little helping hand, they may well draw out all the bonds represented by this equation. Even if this isn't represented in the question, I would recommend you do so because it makes it much easier to count up the bonds, which is what you need to do for this calculation. The other way you'll recognise this question is that they need to give you a table of bond energy values for all the bonds in the question. So we got a bond energy value here for CH, OO double bond, CO double bond, OH single bond. There are 3 stages to the calculation. Step 1, you need to total up the total energy of the bonds broken in the reactants. Step 2, make a separate total for the energy for the bonds made in the products. Step 3, you're just calculating the difference between those, but you have to make sure you do it in the correct order. It's bonds broken minus bonds made. The first thing I've done here is I've made a list of the different types of bond which are broken and made in this reaction. The way I've done that is I've looked at the drawing of the bonds at the top of the question. So there are 4 CH bonds broken in this reactant. There's 2 OO double bonds broken in this reactant. In carbon dioxide, there's 2 CO double bonds, so that's 2 being made. and in two waters there's 4 OH bonds being made, so I've tooled them as well. All I need to do is look up their values in the table and multiply those values up by the correct number for the number of bonds. So I've added those values up and I've got a subtotal for the bonds broken and the bonds made. Last step is just to get the difference. I need to do bonds broken minus bonds made. So the answer here comes out as a minus value, minus 818. That's not a mistake. If you remember back from the start of the topic, all the minus sign in front of an energy value means is that the reaction is exothermic.